In this presentation, I'll be showing how a gene pool can be in Hardy Weinberg equilibrium. Again, all forms of evolution result in changes of allele frequencies. If allele frequencies are changing, some form of evolution is occurring, even if it's just genetic drift. So an interesting fact is, if allele frequencies aren't changing, that means all forces of evolution have stopped. If somehow we can stop all forms of evolution, stop genetic drift, etc., then allele frequencies will remain constant. When this happens, a population, a gene pool, is in Hardy Weinberg equilibrium. And we can use these equations to help us think about what is going on with the genetics and what types of evolution are occurring within a population. So we're going to work through a population here that is in Hardy Weinberg equilibrium, where all the assumptions of Hardy Weinberg equilibrium are holding. So let's start off with a population of 300 individuals, which are going to reproduce. We'll have 200 big L homozygotes. This example is a little different than previous ones in this series of videos, so the numbers are a little different. But we have 200 big L individuals, homozygous dominants, 90 big L heterozygotes, and 10 little l homozygous recessives, for a total of 300 individuals. Now I encourage you to stop the video and, starting from these genotype frequencies, calculate out the frequencies of the big L and the little l allele. And as always, I say, seriously, stop the video, do the math, practice here a minute. Using the gene pool approach, I would say if I have 200 homozygous dominant individuals, I would say those 200 people each contribute 2 big L alleles to the gene pool. The big L, little l heterozygotes, they contribute 2 alleles to the gene pool, 1 big L, 1 little l, and so forth. From these, I can calculate out my frequencies of my various alleles. 300 total individuals, 600 chromosomes or gametes in my gene pool, add up 400 plus 90, 490 big L alleles divided by 600 is going to equal 0.82. 90 plus 20 equals 110 little L alleles. 110 over 600 is going to equal 0.18. Shown graphically, that's what those allele frequencies would look like. So if mating is random with respect to our big L and little l alleles, and there's no natural selection currently happening, so it's not actually beneficial to be able to lactose tolerance, if all the other assumptions are holding, then evolution is going to stop. Our population is going to be in Hardy Weinberg equilibrium, and we can treat it as if our gametes are being mixed up into a single gene pool. It's almost as if all these individuals tossed all of their gametes into a big pool, and they are just swimming together, and sperm are randomly pairing up with eggs. We also need to assume that there's a 50-50 sex ratio. So when I say there's 200 big L individuals, that means 100 of them are male and 100 of them are female, and so forth. So 90 big L little l heterozygotes. In order for this to work, there needs to be 45 males and 45 females, and so forth. And we're going to treat this. So here I have 200 big L individuals. 100 are male, 100 are female. I have 90 big L little L individuals. 45 of them are XY males, 45 of them are XX females. I have 10 total little L individuals. 5 are XY males, 5 are XX females. And again, if selection is not acting on these allele, if all evolutionary processes are stopped, we can act as if they are just tossing all of their gametes into the population, is just tossing all of their gametes into a theoretical gene pool, and that sperm are going to swim around and randomly mate with eggs. Now, the frequency of matings, the types of pairings that are going to result in diploid genotypes, is going to depend on the frequencies of each allele in the gene pool. So we can treat the frequencies of alleles as probabilities. And we can use those probabilities to calculate the likelihood of different pairings in the gene pool. And these pairings are going to determine the frequencies of genotypes in our next generation. So, for example, we can calculate out, based on the frequency of big L sperm and big L eggs, we can calculate out what's the probability that in our theoretical gene pool, a big L egg meets a big L sperm. Now, this is a theoretical gene pool, but if other evolutionary forces are not occurring and mating is random with respect to this gene, then this extrapolation, this theoretical gene pool, is more or less how population genetics play out even in real populations. So this is how we're going to work through the math. We're going to calculate out all the probabilities of different pairings of gametes meeting. So we're going to start off with what's the probability of a homozygous dominant pairing occurring. So that is the probability that a big L egg meets a big L sperm. Now this is equivalent to saying what's the probability that a big L sperm meets a big L egg. It doesn't matter how we say it, it's the same thing. So we can make our notation a little mathier. We can go from the statement, the probability, etc. We can put it in parentheses and say we're talking about the probability that an egg is L times the probability that a sperm is big L. We'll shorten this like the mathematicians do to the probability of L times the probability of L, probability that an egg is L times the probability that a sperm is L. And in population genetics, we shorten it further. We use a symbol, P or Q. In this case, I'm going to be using the symbol P to mean the frequency of the dominant allele, the frequency of L. So the probability that a big L egg meets a big L sperm in our gene pool is the frequency of the big L allele in eggs times its frequency in sperm. So P times P, that's going to be 0.182 times 0.182. This is called the joint probability of these two events occurring. A probability of a big L and the probability of a probability of a big L A or its frequency times the probability of a big L sperm or its frequency. That's going to equal 0.667. So 0.667, that's the probability of a homozygous dominant pairing occurring. Now we can look at what's the probability of a homozygous recessive pairing occurring. That's a little L egg meets a little L sperm in our theoretical gene pool. So we can go from that statement in English to a kind of mathy statement. What's the probability that an egg is L times the probability that a sperm is little L? We can shorten that further to what's the probability that an egg is little L times the probability that a sperm is little L. Or we can just make it Q times Q. We said that our sex ratio was equivalent, so we don't need to keep track of whether it's an egg or a sperm now, as long as our sex ratio is 50-50. We're using Q here to mean the frequency of the little L allele. And so the frequency of our little L allele is 0.18. So 0.18 times 0.18, that is 0.034. That's going to be the probability of a homozygous recessive individual forming. So what is the probability that a big L egg meets a little L sperm? This is the probability of a heterozygote forming. So we've talked about our two homozygous, our homozygous dominant, our homozygous recessive. Now we're going to talk about our heterozygous. Important is there are two ways of this occurring. We can have a big L egg meet a little L sperm, or we'll then talk about what's the probability of a little L egg meeting a big L sperm. First, we'll deal with the first scenario. Big L egg meets a little L sperm. We'll go from that English statement to a mathy statement. Probability that an egg is L times the probability that a sperm is little L. Since we have a 50-50 sex ratio, we can just shorten it to the probability of big L times the probability of L. We're going to do what population geneticists do, which is the frequency of the dominant allele is P, the frequency of the recessive allele is Q. That's 0.82 times 0.18, and that's going to equal 0.150. Now we can flip this around. We can do the same calculations, except instead of P times Q, we're going to get Q times P. Instead of 0.82 times 0.18, we're going to get 0.18 times 0.82, the exact same thing. So there's two ways of making our heterozygotes. They both have a probability of 0.15 occurring. So here are all of our calculations so far. We have our our homozygous dominant, big L, our homozygous recessive, little l, and then our two heterozygotes here. P times P is the probability of a big L egg meeting a big L sperm in our gene pool. Q times Q, probability of a little L egg meeting a little L sperm, and then P times Q, big L egg meeting a little L sperm, and then Q times P, just the reverse, is the probability of a little L egg meeting a big L sperm. Sorry, I think I reversed my colors there. All of these probabilities have to add up to 1 because they represent all of the possibilities that can occur. Again, here, P is the frequency of big L, Q is the frequency of little l. Sometimes these get switched around. You always need to make sure you're understanding how a person for a particular situation is defining things. So if we wanted to write out an equation to represent all of these dynamics, we'd have our 4 different ways of putting things together. We would have big L for our homozygous dominant, our little l for our homozygous recessive, and then our 2 ways of having our heterozygotes. So that is, they all have to add up to 1. So 1 equals P times P plus Q times Q plus P times Q plus Q times P. I often will rearrange these to focus attention on what's going on. So this is now P times Q plus P times Q, just to be explicit about what the terms are. And then I can factor out a 2 from here. I have P times Q plus P times Q, so that is the same as 2 times P times Q. I could put a multiplication sign here if I wanted to. I could get rid of the parentheses entirely if I wanted to. The parentheses help me to indicate that these 2 terms go together. So I can factor out a 2. I get 1 equals P times P plus Q times Q plus 2 times P times Q. And then usually we make this even more compact and we express it as 1 equals P squared plus Q squared plus 2 times P times Q. And that is our typical form of the Hardy Weinberg equation. Though sometimes you'll see it flipped around. We'll put it in the order of homozygous dominant, heterozygous, homozygous recessive. So we get 1 equals P squared plus 2PQ plus Q squared. It's often how it is shown. Now you can use the Hardy Weinberg equation to do the math that I just did previously, but do it more quickly. Instead of writing everything out in a table here, you can just plug your allele frequencies, your original allele frequencies, into the equation. So I know what P is and I know what Q is. So P is 0.82, so 1 equals 0.82 squared. Q is 0.18, so I have 0.18 squared. 2 times P times Q, 2 times 0.82 times 0.18. I can multiply those out, and I get 1 equals 0.67 plus 0.30 plus 0.034. That all equals 1. That indicates my frequencies of each one of my genotypes. So my big L, homozygous dominant genotype should be 0.667. That's what I calculated out here. My homozygous recessive, 0.034, and then the heterozygote is 0.30. And using this equation here just saves you the steps of writing out both of these heterozygotes as I did here. I broke it up into a separate step. You can just simplify it with the equation there. So these are the genotype frequencies of my offspring: 0.067, 0.3, 0.034. Now I can compare the genotype frequencies of my parents to the genotype frequencies of my offspring. And because I stopped all evolutionary processes and mating was random, there has been no change in the genotype frequencies between the parents and the offspring. Big L is 0.67, big L is 0.67, just different rounding here. Big L, the heterozygotes, 0.3, 0.3, and so forth. So the frequency of my genotypes has not changed over time. There's been no evolution occurring. So this is only when rating is random and no evolutionary forces are occurring. Alleles and genotype frequencies will stay constant over time. So if there is natural selection happening, we might expect an allele to increase, but if there is no evolution happening, there's no natural selection, then we would see a constant allele frequency over time. And this situation, again, is called Hardy Weinberg Equilibrium. It is a null model against which to look at what's actually happening in a population and understand what evolutionary processes might be occurring.